This is the college algebra final review. I'm going to be doing 18 problems from your review. These are the 18 problems that will be on your final. The final review consists of 28 problems, but only 18 of those will be on the final. The final is comprehensive, which means it covers chapters 1 through 6. All right, so the first problem we're going to do is number 1 on the review. This is a division of complex numbers. So it says divide and express the result in standard form. So to divide two complex numbers, you multiply numerator and denominator of the fraction by the conjugate of the denominator. And the conjugate of a complex number is found by changing the sign of the imaginary part, so the part that has the I in it. So we need to multiply this fraction, numerator and denominator, by 6 plus 8i. So I'm going to do that. Now I carry out the two multiplications. In the numerator, it's the distributive property. We're going to distribute the 9i across the 6 and across the 8i. So we get 9i times 6 plus 9i times 8i. And in the denominator, when we multiply a complex number by its conjugate, we get the sum of the two squares. The outside plus inside terms are going to add to 0, and then you're going to get minus something squared times I squared, but I squared is -1. So to find the denominator when we divide two complex numbers, all we have to do is square the first number, so square the 6, and then square the 8 and add those two things together. That's the reason we multiply by the conjugate, because when we multiply a complex number by its conjugate, we get a real number. So what I get is 9i times 6 is 54i plus 72i squared. And I note right then and there that the I squared is going to be -1. And in the denominator, I'm going to get 36 plus 64, which will be 100. So I have now 72i squared is going to be -72 plus 54i over 100. And my math lab is not going to accept this as a correct answer. Now you know that I will accept this as a correct answer, but you need to go ahead and simplify if you can. And in the 72 and 100, right here, I can cancel a common factor. There's a common factor of 4 in 72 and 100. So I would get -18 over 25 when I cancel the 4 from the -72 and the 100. In the 54 and 100, there is a common factor of 2. So when I cancel the common factor of 2 in the 54 and the 100, I get 27 over 50. And that's 27 over 50i. So the correct answer to this problem is -18 over 25 plus 27 over 50i. That is written in the correct form as a complex number. The next problem we're going to do is number 5. Solve the absolute value inequality. This is a greater than type absolute value inequality. And you learned that if you have an absolute value type, greater than type absolute value inequality, this means that the stuff inside the absolute values either has to be less than -12 for this inequality to be true, or the stuff inside the absolute value inequalities has to be greater than +12 for this inequality to be true. So to solve a greater than type absolute value inequality, you take the stuff inside the absolute values, the 3x minus 6, and you set it less than the negative constant. Then you take the stuff inside the absolute value inequalities and you set it greater than the positive. And then you solve these two inequalities. And they do want you to write this in interval notation once you have the two inequalities solved. So I'm going to add 6 to both sides of this first inequality. And I get 3x is less than -6. And then divide by 3. And I get x is less than -2. Now I'm going to solve the other one. I'm going to add 6 to both sides. I get 3x is greater than 18. I divide both sides by 3, and I get x is greater than 6. So what is the interval notation for this? So x is less than -2 means all the numbers to the left of -2. So in interval notation, that's all the numbers from -infinity to -2. For x is greater than 6, that means all the numbers to the right of 6. All the numbers to the right of 6 we denote as 6 to infinity. And we're going to join those with a union symbol. The next problem we're going to do is number 6. Use the graph to determine the following: the function's domain, the function's range, the x-intercepts, if there are any, the y-intercepts, if any, and the function values at -1 and +3. First of all, what is this function's domain? Because the arrows are pointing both to the left and to the right, that means that this function continues horizontally to -infinity and to +infinity. So the domain of this function is the set of all real numbers, or from -infinity to +infinity. But what's the range? Well, this function has a top limit. It does not go beyond -3. It comes from -infinity and it stops at -3. There are no values of this function larger than -3. So the range of this function's -infinity to -3. And we need to use a bracket. I know there's always been some confusion about that. But we need to use a bracket on that -3 because that point is on the graph. So that point, what is that, 1, -3, is on the graph of this function. So we use a bracket to denote that that point is included in the range of this function. All right, x-intercepts. Are there any x-intercepts? And the answer is no. This function's not crossing the x-axis anywhere. So there is no x-intercept. If we were crossing the x-axis, we'd determine by looking at the graph what those two values are. Just like we're going to do that for the y-intercept. So in my math lab, you'll be able to blow this graph up so that you can see it a little clearer. But the y-intercept, this graph is crossing at -4. So the y-intercept is -4. All right, last but not least, to determine the value of this function at -1 and 3. So I'm just again, in MyMathLab, you'd be able to blow this up so that you could see it a little bit clearer. But -1 is right there. And if I go down and intersect where x is -1 with the graph of this function, I can see that when x is -1, y is -5. So the value of this function at -1 is -5. So I'm going to type that in. And 3, again, where's x equals 3? Right there. And if I go down where that intersects the graph, I can see that also when x is +3, the value for y, or the value of this function, is also -5. The next problem we're going to do is number 7. Use the graph to determine the open intervals. And MyMathLab even tells you that the intervals are open, which means you are going to use parentheses on your intervals. So open means parentheses, no brackets. Use the graph to determine the open intervals on which the function is increasing, if any, the open intervals on which the function is decreasing, if any, the open intervals over which the function is constant, if any. And this function's not going to be constant anywhere. All right, so where is this function increasing? The function's increasing wherever the graph rises from left to right. And the graph is rising from left to right, right in here. Let's highlight that in red. And it's increasing right in here. We'll highlight that in red. Those are the two places, two intervals over which this function is increasing. So we always write increasing and decreasing over the domain of the function. So we use values for x in our intervals. So it looks like it's increasing from -∞ to 0, and then it stops increasing. And MyMathLab does tell me to separate the intervals using commas. So it tells me to use a comma. So we're going to put a comma there. And then it's going to be increasing what, from 1 to 2? Again, you always use values over the domain to describe where a function's increasing or decreasing. All right, where is this function decreasing? Well, it looks to me like it's decreasing from 0 to 1. Let's highlight that in blue. And it also looks like it's decreasing to the right of 2. So where is this function decreasing? Well, it appears to be decreasing from 0 to 1. Use a comma to separate those two intervals, and from 2 to infinity. And that is positive infinity, not negative infinity, because we're talking about over the domain. So where is this function going in the domain? Well, it starts at 2 and it goes to the right forever. So it's 2 to infinity. All right, so where is this function decreasing? Well, this function is not decreasing anywhere. Excuse me, constant, so sorry. Where's the function constant? It is not constant anywhere. It's either increasing or decreasing over its entire domain. The next problem we're going to do is number 9, find the domain of the function. When we have a rational function like this, and this is a rational function because we have variables in the denominator of our fraction, remember that you cannot let the denominator of a fraction be 0. 0 in the denominator of a fraction is undefined. So x cannot be 3, or x minus 3 cannot be 0. It can't. And x minus 5 also cannot be 0. You cannot let the denominator of a fraction be 0. So x minus 3 cannot equal 0. X minus 5 cannot equal 0. So x cannot equal 3. X cannot equal 5. It can be anything else, but it cannot be 3, and it cannot be 5. So which of these 4 choices describe that? Well, it's not A, because A says x can be anything, and that is not true. X cannot be anything, any real number. It can't be. It can't be 3, and it can't be 5. How about B? Well, B excludes 3. It says you can go from negative infinity to 3, skip over 3, and then 3 to infinity. But it doesn't exclude 5, so it can't be B. How about C? C excludes 3 because you come from negative infinity, you skip over 3, then you go to 5, you skip over 5, and then you go to infinity. So the only answer it can be is C. Again, looking at the number line, this looks like this. You have wholes at 3 and 5. Anything to the left of 3 is okay. Anything between 3 and 5 is okay. Anything to the right of 5 is okay. But anything else, 3 and 5 have to be excluded. All right, problem 10 is the next problem we're going to do, finding the inverse of a function. So first of all, find the inverse. To find the inverse of a function, the first thing you do is just rewrite this. Instead of using f of x, you use y. F of x and y are the same thing. So we just rewrite this in terms of y. And then the inverse of a function interchanges the domain and range. That's what it does. So you interchange x and y. So where there's a y, you write an x. And where there's an x, you write a y. And that is the inverse. However, we do need to solve this for y to determine if the inverse is a function. All right, so we need to solve this for y. And I'm going to do that by adding 3 to both sides. And then divide by 7. And that is a function. As a matter of fact, it's a linear function. Move myself out of the way here. It is a linear function because the exponent on the x is 1. So both the function and its inverse are linear, they're lines. So let's go ahead and type in the x plus 3 over 7 is the inverse. And then we need to determine the graphs. And as you recall, when we went over this in class, we did this by excluding the graphs that do not fit our scenario. For example, graph A does not fit our scenario because both our graphs are lines, but both these lines have positive slope. The slope of my function is 7. The slope of my inverse is 1 over 7. And is that a coincidence? And the answer is no. They are going to have reciprocal slopes if they are inverses of each other. So A cannot be the answer because the blue line, which is the line of my function, has a negative slope. It's going down. It can't be A. Now let's look at B. Well, B looks correct because both the slope of my function and the slope of my inverse are positive. So B looks promising. Let's go look at C. Can't be C because the graph of both the function and its inverse in C has negative slope. They're both going down. Can't be C. Can't be D because the slope of the function's correct, it's going up, but the slope of the inverse is going down. The slope's going to have to be positive for the inverse. So it can't be A, can't be C, can't be D, it must be B. And that looks correct to me anyway. It does look like there are reflections about the line y equals x, and it does look like the function of my line, the slope is fairly steep, which 7 is a pretty steep slope. And the slope of the inverse, which is 1/7, is not a large slope, so you would think that it's not increasing too rapidly. So that does look like the correct problem, the correct answer to me. All right, domain and range. Well, the domain of, looks like I'm having sharing issues. Let me reshare this. All right. Okay, I think I'm good now. All right, so back to what I was saying, domain and range. Both of these are lines. And the domain and range of a linear function is the set of all real numbers. So the domain and range of the function and the domain and range of the inverse is going to be the set of all real numbers. And you should be able to just look at these two graphs. As a matter of fact, even though A, C, and D are incorrect graphs, they do show that the domain and range of both of these functions is the set of all real numbers. They're linear. The domain and range is going to be the set of all real numbers. The next problem we're going to do is number 11, quadratic function. Consider the function f of x equals negative 2x squared plus 8x minus 3. Determine without graphing whether the function has a minimum value or a maximum value. Well, it's going to have a maximum. And how do I know that? Well, I know it's going to have a maximum because I know this thing opens down. And how do I know it opens down? Since the coefficient on the x squared is negative, it opens down. And if it opens down, it's going to have a maximum. Then it asks me, well, what's that maximum value? Well, I need to find the vertex to determine what the maximum value is. The y value of the vertex is its maximum. But first I have to find the x value because that's what I have a formula for. The x value of my vertex is minus b over 2a. So I need to find x first so that I can plug that back into the function and find y. So what's b? Well, it looks like b is 8 and a is negative 2. So we're going to plug those in. And I do believe that is 2. So the maximum occurs at x equals 2. But what is that maximum value? Well, we need to evaluate the function at 2 to determine the maximum. So the maximum is the function evaluated at 2. So we're going to plug in 2. And my handy dandy calculator says that is 5. So the maximum is 5 and it occurs at 2. What's the domain of this function? Well, the domain of every quadratic function is the set of all real numbers. What's the range? If it's a quadratic function that opens down, which this is, the range is going to be from negative infinity to whatever the y value of the vertex is. So it's going to be negative infinity to 5, and we have to use a bracket because the point 25 is on the graph of this quadratic. It's the vertex. So the range will be from negative infinity to 5. All right, we're going to skip 12 and we're going to do problem 13 next. Problem 13, find all the zeros of this polynomial function. And then it gives you some suggestions. It tells you to use the rational zeros theorem, Descartes' rule of signs, possibly graph it to find a zero. Any of those suggestions are great. You know, for example, Descartes. If I look at this function, it looks to me like I have 2 sign changes. So I have 2 or that number less an even integer. So 2 minus 2 would be 0. 2 or 0 positive real zeros. So either 2 of them are positive or none of them are positive. Now let's look at f of negative x. And it looks to me like we have only 1 sign change. So I do know that one of my zeros is a negative number. I do not know that for sure. Okay, so now let's look at the rational zeros theorem. The rational zeros theorem says that if I have a zero of a polynomial function and it's a rational number, it's going to be a ratio of factors. It's going to be the ratio of the factors of my constant over the factors of my leading coefficient. So in this particular case, the constant is 21 and the leading coefficient is 1. So we just need to look at factors of 21 because it would be factors of 21 over factors of 1. So what are the factors of 21? We're not going to do problem 14, so I'm just going to write over the top of it. Well, that would be what? Plus or minus 1, plus or minus 3, plus or minus 7, and plus or minus 21. So I would venture to say that one of my zeros is either 1 or negative 1, 3 or negative 3, 7 or negative 7, or 21 or negative 21. Now, I could certainly graph this. You either have a TI-84 calculator at your disposal, or you've downloaded the TI-84 emulator. I sent you a link in your announcements that you could do that free for 6 months. And since you can do that, you can use that on your final exam if you so desire. So you could graph this if you wanted to. I don't know that it's necessary. I mean, I'm just going to check 1 and see if that works. And I'm going to check 1 using synthetic division. So I'm going to write that down here. So I'm going to write the coefficients of my function, 1, negative 5, negative 17, and 21. And then I'm going to bring the 1 straight down. 1 times 1 is 1. Add that together. Negative 4 times 1 is negative 4. Negative 21 times 1 is negative 21. So it does look like 1 is one of my zeros. Now the third row in my synthetic division is going to give me my quadratic equation. If 1 is a 0, x minus 1 is one of the factors of this polynomial. So this quadratic down here is the other factor. So I'm just going to write that quadratic. And I'm going to set it equal to 0. That'll help me find the other 2 zeros. You could certainly use the quadratic formula on this. It is factorable, which is what I prefer. If I can factor it, I'm going to factor it instead of using the quadratic formula, because quadratic formula just has lots of places where you can make errors. So what do we have? Minus 7 plus 3. Do a quick FOIL in my head to make sure that's correct. Negative 7x plus 3x is negative 4x. Negative 7 times plus 3 is negative 21. So we're going to set each factor equal to 0. So we get what? 7 is a 0, and negative 3 is a 0. And sure enough, what Descartes told me is true. Descartes said that one of my zeros was going to be negative. One of my zeros is negative. Descartes told me that the other 2 were either positive or they were going to be complex. That's what that 2, 0 means. Either they're positive or none of them are positive, means they would be complex. So I do have 2 positive zeros and a negative 0, and they are all factors of my constant. So my zeros are 1, 7, and negative 3. All right, the next problem we're going to do is problem 16. Solve the polynomial inequality and graph the solution set on a real number line. Express the solution set in interval notation. All right, to solve, this is a polynomial inequality, and to solve it, we need to find these things we call boundary points. So what we need to do is we need to solve the equation 3x squared plus 17x minus 6 equals 0. And that'll give us the 2 numbers that separate my number line into intervals. So I'm going to solve this real quick. And that is solve. We can solve that by factoring. You could certainly use the quadratic formula, but the problem you're going to have on your final will be factorable. That looks like that's going to be a 6 there and a plus and a minus 1. That looks correct to me. Let me do a quick FOIL in my head. Minus x plus 18x is 17x. Minus 1 times 6 is negative 6. So we're good to go. So what are my 2 points that separate my number line into intervals? Well, I need to set each one of these factors equal to 0. All right, when I add 1 and divide by 3, I get x is 1/3. And when I subtract 6, I get x is negative 6. So let me go down here where I have a little space, and let me draw my number line, set up my intervals, and pick my test points. All right, so we have 2 boundary points. We had negative 6 and 1/3. So these 2 points break my number line up into 3 intervals from negative infinity to negative 6, excuse me. And let me go back up real quick and let me look at this inequality. It is less than. So I'm going to have parentheses on everything, no brackets, because at no point am I going to have equals, because it's just a less than. So no brackets. So the next interval would be from negative 6 to 1/3, and then from 1/3 to infinity. All right, so now we're going to set up our little table, and we're going to pick our test points, and let's see what happens. All right, so my intervals are negative infinity to negative 6, negative 6 to 1/3, and 1/3 to infinity. Pick my test point, my test value. Negative 7 is to the left of negative 6, so why not use it? Between negative 6 and 1/3 is 0, and 0 is the easiest number to test, so I'm going to use that. And then anything to the right of 1/3, well, I'll pick 1. All right, and then I need to evaluate this function at each of these test values and see what happens. Okay, so when I evaluate my function at negative 7, I got 92, which is greater than 0. That's not what my inequality said. My original inequality said less than 0. So that's a failure. So the conclusion is that this is false, because my inequality said it's less than 0, and for that test point, it's greater than 0. All right, let's try 0. When I evaluate this function at 0, I get negative 6. Well, negative 6 is less than 0, so that's true. And then when I evaluated at 1, I got 14. That's greater than 0, and that is false. So the only place where this inequality is true is between -6 and 1/3. Because if it's true for the test value in that interval, it's true for every point in that interval. If it's false for a test point in that interval, it's false for every point in that interval. So the solution to this is the interval from -6 to 1/3. All right, so which of these graphs is from -6 to 1/3? Well, it's G, isn't it? It's not A, and it's not A because A has brackets. There are no brackets in the solution set of this inequality because we had less than, not less than, or equal to. It's not B because the interval doesn't go from 1/3 to 6. It goes from -6 to 1/3. It's not true for C because it's the interval between 2 points. It's not true for D, not true for E, not true for F. And obviously it's not true for H. There is a solution to this inequality. All right, so since we're in the solving inequalities mood, let's solve problem 17, which is a rational inequality. And the only difference between this one and the one we just did is you get one more boundary point from the denominator. So the numerator, if we just look at that, what two values would make the numerator equal to 0? Well, if I set x plus 7 equal to 0, I'd get -7. So if x is -7, the numerator is equal to 0, that's a boundary point. So let's write that down. If I set x minus 9 equal to 0, then that would be x is 9, x equals 9, so that's a boundary point. And looking at the denominator, if I set that equal to 0, I'd get -5, so -5 is a boundary point. So what I have here, if I look at the number line, -7, -5, and 9, I have these intervals here. Okay? So what are these intervals? Well, the first interval is everything to the left of -7. So that would be -infinity to -7. And let's pause a minute. Bracket or parenthesis on the -7. My inequality is less than or equal to. So you're going to include any value that would make the numerator equal to 0. So you're going to put a bracket if you got that point from the numerator. If you got that boundary point from the numerator, put a bracket next to it if you have less than or equal to or greater than or equal to. So we're going to put a bracket. The next interval is from -7 to -5. But I cannot put a bracket next to -5. I have to use a parenthesis because -5 is the value I got from the denominator. You never use a bracket on a value you get from the denominator because the denominator cannot equal 0. Then we have what? -5 to 9, bracket on the 9, and from 9 to infinity. All right, so now I need to pick test points in each of these intervals and evaluate the function at each of these test values. All right, so let me see if I got room here to do this. Let's do it down here because I'm not going to do problem 18. So the intervals are from -infinity to -7. So I just picked -8. That's to the left of -7. And then we have from -7 to -5. -6 is between -7 and -5, so I'd use that. And the next interval's from -5 to 9. And I'd pick 0 because it's the easiest point to test. And then from 9 to infinity. And I just picked 10. Okay, so what's my result? And use your calculator. Let your calculator do this. I did. I didn't calculate this by hand. I put this in my calculator and let my calculator do it. So for -8, I get -136/3, which is less than 0, which is what my inequality is. It's less than, so it's true. -6, I got 15. 15 is greater than 0, so that is false because my original inequality is less than. For 0, I get -63/5, which is less than 0, so that is true. And when I evaluated it at 10, I got 17/15, and that is greater than 0, so that is false. So the solution is the union of these two sets where the inequality is true. So my solution is from -infinity to -7 with a bracket, and from -5 to 9. All right, so which graph is that? Well, it's not A, because I have a union between a set that's infinite and a set between two numbers. It's not B, it's not C. D? D looks correct to me. Can't be E, and it's not the set of all real numbers. So it looks to be D to me. All right, problem 19. We're going to do 19, 20, and 21 because it's time for logarithms. So we're in chapter 4. We finished chapter 3 with the last problem. Now we're in chapter 4 where we deal with logarithms. In problem 19, this is that problem where you first write it as an exponential and you type that in and then you solve it for x, and that's your second answer. So you get two parts to it. The first part is just to write it as an exponential. Second part is to solve the equation. All right, so let's write this as an exponential. Log base 3 of x minus 2 equals 2. So the base is 3. Whatever the log is equal to, that is the exponent on the base. So it's equal to 2. So that is the exponent. And that's equivalent to whatever you're taking the log of. So the first answer is 3 squared equals x minus 2. Now you're going to solve that. So we get 9 is x minus 2, add 2 to both sides, and it looks like x is 11. All right, problem 20 is to condense logarithms into a single logarithm, and this is a subtraction, so you're going to have a quotient. The first thing we're going to do, if I have a constant outside a logarithm, I can take that in as a factor. So that's going to be the natural log, and that is ln. Someone on their exam typed in. It is not an I. It's a lowercase l. Natural log L. So ln x to the 6th minus ln y to the 5th. So we can take each of those factors out of, or take them into the logarithm as exponents. And then you have the difference of two logs. The difference of two logs is the log of the quotient. So this is the log of x to the 6th over y to the 5th. All right, problem 21. Solve the following exponential equation by expressing each side as a power of the same base and then equating those exponents. So you need to write the 1/4 as 2 to the something. All right, so what is it? Well, it's 1 over 2 squared. 4 is 2 times 2. But if I have an exponent in the denominator of a fraction, I can take that to the numerator by changing the sign of the exponent. That's one of your laws of exponents that you got 8th grade, somewhere 9th grade, I don't know, a long time ago. So what we have is 2 to the 6 minus x is 2 to the minus 2. And once the bases are the same, you can set the exponents equal to each other. So we have 6 minus x equals -2, and then solve that equation. I'd probably subtract 6 from both sides, and then divide by -1. And that looks like x is 8. All right, problem 22. Solve the following exponential equation. Express the solution in terms of the natural logarithms or common logarithms. Then use a calculator to obtain a decimal approximation for the solution. So you're going to solve this first exact in terms of logarithms, and then you're going to take your calculator out and get a decimal approximation to it. So to solve an exponential equation, you have to have the exponent part completely isolated by itself on one side of the equation. So I must get rid of the 2 on the left-hand side. And I can do that by dividing both sides by 2. So I get e to the 3x equals 1,322 divided by 2 is 661. Now I can take the natural log of both sides. And when I take the natural log of e to the anything, it's just the exponent. Because what does the logarithm mean? The logarithm means, what do I raise that base to get that value? Well, the base of the natural logarithm is e. So what do you raise e to get e to the 3x? 3x. So what we have here is 3x equals the natural log of 661. Divide both sides by 3. And there is the exact value. The exact value is the natural log of 661 divided by 3. All right, so then you take your calculator out, and you're going to find a decimal approximation to this value. So you'd find your LN button on your calculator. And when you click that button on your calculator, it opens parentheses for you. You type in the 661, close the parentheses, then divide that by 3. And when I did that, I got 2.16. Now, on your hourly exam, I had lots of problems with this one. You had lots of problems. Round off errors, lots of round off errors. Or you didn't round it off to the correct number of decimal places. MyMathLab gives you instructions on how many decimal places to round off to. It says 2. So what I do when I do this calculation is I look at the digit in the third decimal place. Look at that digit. If that's 5 or above, you round the number to the left up. If it's 4 or below, you leave the digit in the second decimal place alone. So the number to the left, you leave it alone. So be sure you round off correctly, and you round off to the correct number of decimal places. All right, problem 23. We're getting close to the end here. Solve the logarithmic equation. Be sure to reject any values of x that are not in the domain of the original logarithmic expression. So if I get anything that's negative, I have to reject it, because log base 7x, x cannot be a negative number. You can't take the logarithm of a negative number. Give an exact answer. So first of all, we need to combine or condense these two logarithms into a single logarithm. Once it's written as a single logarithm, I can write it as an exponential, and then I can solve it. So this is the sum of two logs. The sum of two logs can be combined by taking the log of their product. So we can write this as the log base 7 of x times 6x minus 1. And that is equal to 1. So now we're going to write this as an exponential. So that base is 7. We're raising that to the first power. Whatever the logarithm is equal to, that's my exponent that I raise my base to. And that's equal to x times 6x minus 1. And then that's quadratic, and I need to solve it. So what do we got here? I'm going to use that reflexive law of equals and write this in a different order just because it's easier for me. Then I'm going to distribute the x across, subtract the 7 from both sides, and now solve this. And I believe this is factorable. Seven here, 1 there. I think that is correct. So we get 7, 6, x equals 7, 6 if I set that equal to 0, and x equals -1 if I set that equal to 0. And it can't be -1. That is not in the domain of the original equation, so the solution is 7, 6. Okay, we're going to skip 24 and go to 25. This is solving a system of nonlinear equations. We have x squared plus 2y squared equals 144, and x plus y equals 12. This is an ellipse. The top equation is an ellipse. The bottom equation is a line. So you could have an ellipse and a line intersecting in 2 different places. So I'm going to use substitution to solve this. I'm going to solve the second equation for x, and I'm going to plug that into the first equation. So we're going to solve this for x. And I do that by subtracting y from both sides. Now I'm going to plug that in for x in the first equation. So I get 144 minus 24y plus y squared is equal to 144. 144 minus 24y. I think I lost a y squared. Sorry about that, folks. Plus 2y squared equals 144. Is that better? 144 minus 24y plus y squared plus 2y squared. I just left the 2y squared off there. Okay, so that's going to give me a 3y squared. And when I subtract the 144 from both sides, I end up with -24y plus 3y squared is 0. And so all I can do here is factor out a y, and I'm going to do that. So I get either y is 0 or -24 plus 3y is 0. Add 24 to both sides. Divide by 3, and I get y is 8. So I get either y is 0 or y is 8. And I had solved the second equation for x. So I'm just going to plug those 2 values for y back into this equation to find my 2 values for x. So if y is 0, x is 12 minus 0, or x is 12. So one of my ordered pairs is 12, 0. If I have y equals 8 and I plug that in, I get x is 4. So my other ordered pair is 4, 8. All right, problem 26 is graphing a system of linear inequalities. And I would graph personally both of these using intercepts. It's just going to be so easy for me to graph that way. You could certainly solve for y and use the slope and the intercept, that's just more work than I'm willing to do. So that first one, we have 2x plus 4y. If we graph the line, the x-intercept would be 2. The y-intercept would be 1. So I am going to graph those. And I would graph this in MyMathLab as a solid line because I do have less than or equal to. So it would be a solid line. As a matter of fact, they're both going to be solid lines. All right, the second inequality, the x-intercept is also 2, and the y-intercept is 8. Okay, so now I need to figure out where to shade, because the solution set to a system of linear inequalities is a plane of numbers, so it's an infinite number of ordered pairs. So what we've been doing is we've been testing the origin in both of our inequalities to determine if it makes the inequality true. If it does, you shade the region that contains that value. So you actually have 4 regions, 1, 2, 3, and 4. One of those 4 regions you're going to shade. So I'm going to pick 0, 0 as my test point. And it is true in both inequalities. If I replace x and y with 0, both inequalities will be true. So I'd take my bucket tool and I would shade region 3. Last problem, Cramer's rule. 2 by 2 system using Cramer's rule. Okay, so Cramer's rule. You could certainly do this using addition. I'm not going to grade you if you don't use the Cramer's rule on this, but I'm going to use Cramer's rule. Right, Cramer's rule, we need to find 3 determinants. The first determinant we need to find is the determinant of the matrix formed by the coefficients on x and y. The second determinant we need to find is the determinant formed by replacing the x column, the first column, with our constants, 4, 14. The third determinant we need to find is the determinant formed by the matrix when we replace the y column with our constants. Now you could plug these into your calculator. Finding the determinant of a 2 by 2 matrix is pretty easy, so calculator is probably not necessary. You multiply the main diagonals together, so 4 times 4. Then you subtract the product of the other diagonal. And you do go from left down right first, and then from the upper right to the lower left second. So it's the main diagonal, 4 times 4, subtract from it the product of the other diagonal. So this looks to be 16 plus 6, which is 22. All right, do the same for the next one, 4 times 4 minus 2 times 14. So that is 16 plus 28, which is 44. And then we have 4 times 14 minus 4 times 3. And I didn't actually write down the intermediate value of that. What is 4 times 14? 56. 56 minus 12 is 44. All right, to find x, we take d sub x and divide it by d, which was 44. divided by 22, which is 2. And to find y, we take d sub y divided by d, which is 44 divided by 22, which is 2. So our solution is the ordered pair 2, 2. And that concludes the final review. Again, 18 problems. We've done those 18. It is comprehensive, covers from chapters 1 through 6. You'll have 75 minutes to complete it, and it'll be available early next week, which would be the week of May the 4th. That's our final week.